Okay, welcome everyone to this deep dive. We've got quite a stack of sources here, and today we're tackling one of the universe's really big mysteries, dark matter.
It absolutely is.
Yeah.
It's a puzzle that sits right at the edge of our understanding of, well, everything.
Right. And our mission really is to unpack this dark matter hypothesis. What is it? Why are scientists so sure it's out there when we can't, see it or touch it?
And why finding it directly is proving, well, so incredibly difficult.
Exactly. And there are some genuinely surprising things in here about the cosmos. It really all began with a pretty simple observation, didn't it? Things not quite adding up.
That's right. You look at galaxies, and they're just spinning too fast for the amount of stuff we can actually see.
Yeah, let's trace that back. It starts way back in the 1930s with Fritz Zwicky.
Correct. Fritz Zwicky. He was studying the Coma Cluster, this enormous group of galaxies.
And he noticed something odd about how they were moving.
He did. He saw the galaxies were zipping around much faster than they should have been, given the gravity from all the visible stars and gas he could account for.
Like they should have just flown apart.
Pretty much, yes. It was like a cosmic merry-go-round, spinning dangerously fast. Zwicky calculated the mass needed to hold it all together gravitationally.
And it was way more than what was visible.
Vastly more. So he proposed this unseen stuff, this Dunkelmaterie.
German for dark matter.
Precisely. To provide the extra gravity.
And that wasn't just like a one-off strange finding in one cluster, was it?
No, not at all. Decades later, in the 1970s, Vera Rubin and her colleague Kent Ford provided really crucial evidence.
Vera Rubin. Looking at individual galaxies this time.
Yes, spiral galaxies like Andromeda, which is relatively close to us. They measured how fast stars were orbiting the galactic center.
And intuitively, you'd think the farther out stars would move slower, like planets in our solar system. Mars moves slower than Earth?
That's the standard gravitational expectation, yes. But that's absolutely not what they found.
What did they find?
They observed what are called flat rotation curves. The stars, way out on the edges, were orbiting at roughly the same high speed as stars much closer to the center.
Which makes no sense with just the visible matter.
It makes no sense at all unless there's a lot more mass there than we can see. An invisible halo of mass spread throughout the galaxy, especially in the outer parts.
Providing that extra gravitational glue.
Exactly. That's the dark matter halo. It interacts via gravity, holds things together, but it doesn't seem to emit or interact with light in any way we can detect, hence dark.
Okay, so we infer it's there from its gravity. And the scale of this stuff, our sources suggest it's, well, huge.
It's genuinely mind-boggling. Based on various cosmological measurements like the cosmic microwave background, galaxy clustering, gravitational lensing, the standard model suggests dark matter makes up about 27% of the universe's total mass energy?
27%. Compared to ordinary matter, us planets, stars, which is only about 5%.
That's right. 5% is everything we know and see directly. The vast majority is dark matter, and even more is dark energy, which is a whole other mystery. But yeah, 27% is dark matter.
Wow. Okay, so if it's not ordinary matter, and we can't see it, what on earth could it be? Any ideas?
That is the multi-billion-dollar question. The leading theories point towards new types of elementary particles, things not in our current standard model of particle physics.
Like what?
Well, a long-standing favorite candidate is the WIMP, the weakly interacting massive particle.
Weakly interacting, meaning it barely notices ordinary matter.
Exactly, except through gravity and maybe the weak nuclear force. Then there are other ideas, like extremely light particles called axions, or maybe hypothetical sterile neutrinos. Lots of possibilities.
But finding any of these, well, it's proving tough.
Oh, incredibly tough. You have these amazing direct detection experiments like Exion N1T or LUX or Pandax buried deep underground.
To shield them from cosmic rays and other noise.
Right. They're essentially big, ultra-pure detectors waiting, hoping for a dark matter particle to occasionally bump into one of their atomic nuclei. A tiny signal.
And so far,
nothing definitive. They've ruled out some possibilities and put strong limits on others, but no discovery yet.
But even without a direct hit, the indirect evidence seems pretty strong. You mentioned gravitational lensing.
Yes, lensing is a powerful piece of the puzzle. Massive objects warp space-time, bending light that passes nearby. We see light from distant galaxies distorted by foreground galaxy clusters way more than the visible mass can account for.
The gravity is stronger than it looks.
Much stronger. It implies there's a lot of unseen mass doing the heavy lifting, gravitationally speaking.
And there's the bullet cluster example, which often comes up.
Ah, yes, the bullet cluster. It's a fantastic natural experiment. You had two galaxy clusters collide.
What happened?
Well, the ordinary matter, mostly hot gas, collided, slowed down due to electromagnetic forces, and sort of got stuck in the middle. But when you map the mass using gravitational lensing...
The mass isn't where the gas is.
Exactly. But the bulk of the mass, mapped by lensing, sailed right through the collision, seemingly unaffected, on either side of the slowed down gas. That's just what you'd expect if most of the mass was dark matter that doesn't interact electromagnetically.
It passed through like ghosts while the ordinary matter crashed.
A very good analogy, yes. It strongly suggests the gravitational mass and the visible interacting mass are separated.
Okay, that does sound compelling. Now, our sources do mention alternatives, right? Like MOND.
Yes. Modified Newtonian Dynamics, or MOND. It proposes that maybe we don't need dark matter. Maybe gravity itself behaves differently on very large galactic scales where accelerations are tiny.
Modifying Newton's laws instead of adding new stuff.
Sort of, yes. And MOND actually does a surprisingly good job explaining those flat galaxy rotation curves that Vera Rubin found.
So why isn't it the leading theory?
Well, it runs into trouble explaining other things, like the dynamics within galaxy clusters, the gravitational lensing evidence, especially in cases like the bullet cluster, and also the detailed patterns we see in the cosmic microwave background radiation.
So dark matter seems to fit a wider range of evidence.
Currently, yes. Despite the frustration of not having found the particle yet, the cold dark matter hypothesis seems to provide a more consistent framework across all these different cosmic scales. Its gravitational effects just seem to be everywhere.
Okay, so let's recap. We started with Zwicky noticing galaxies moving too fast in the Coma Cluster, coining Dunkelmateries.
Then Vera Rubin's work solidified it with those flat rotation curves in individual galaxies, showing stars orbiting too fast.
Leading to this idea of unseen mass dark matter making up maybe 27% of the universe, way more than the 5% of ordinary matter we see.
And the hunt is on for what it could be WIMPs, axions, other weird particles using deep underground detectors, though no luck directly yet.
But powerful indirect evidence exists, like gravitational lensing bending light too much, and especially the bullet cluster where visible matter and the bulk of the mass got separated during a collision.
And while alternatives like MOND exist and explain some things, dark matter still seems to be the best fit for the whole cosmic picture we observe.
So thinking about what this means for you, our listener,
Yeah.
It's pretty profound, isn't it? There's this invisible cosmic web, this scaffolding holding the universe together.
Absolutely. It dictates how structures form and evolve.
Yeah.
Figuring out what it is could unlock fundamental new physics.
It really makes you wonder, if 95% of the universe is dark matter and dark energy, what else might be out there, completely hidden from our current view?
What else are we missing? That's the big question that keeps cosmology exciting.